Okay, welcome everybody to another of our JILA Colloquia. This time it's going to be given by Professor John Bohn, one of our very own for a number of decades. We came to JILA probably about the same time.
We did, yeah.
It was a little time ago.
Yeah.
And John, of course, has done a lot of seminal work in cold collisions, but particularly quantum cold collisions, things where we're studying interactions in things like Bose-Einstein condensates or things that are very, very close to absolute zero, and the energy exchange in these collisions is extremely minuscule, and there are a lot of intricate and fine things that happen. And I think enough said, John. Would you? The other thing I would like to mention is that John will be our next JILA chair, so this is coming up. Yes, exactly.
But don't hold that against me.
Okay, take it away. Fun with ultra-cold molecules.
Fun with ultra-cold molecules. So I feel like parts of this will probably stretch your definition of fun, but we'll see as the time goes along. Before we get to the cold molecules even, I want to step back and make some broad remarks about, frankly, about science and why we do it. And you may find yourself thinking, what is science? What's it for? What's it about? And if you follow the news, you will find that there seem to be two reasons to do science, two primary reasons. And they're like this. On the one hand, you could say, well, we're doing science to apply it to something. We want to build a gadget. We want to make better solar cells. We want to build quantum computers or whatever. And that's fantastic. Physics is all about being useful for very important things. Look at me. I'm broadcasting this on a screen. Thank you, physics. On the other extreme, you say, well, no. Physics is done, science is done for very fundamental reasons. It is the deepest intellectual journey of humanity to understand, to peer into the mind of God, to say, what's next for the Standard Model? What's inside a black hole? This kind of thing. And these are both fantastic and legitimate reasons and motivations for doing science. And I will add that the scientists at JILA are second to none at doing both of these processes. You know this. But I will also say that from the point of view of the average ordinary scientist on the street, there's a whole spectrum of motivations in between these two great things. And most scientists, frankly, are somewhere on the spectrum. So what I'm going to talk about today are things we do because we think they're cool, because we just want to know, right? You know what I'm talking about. In your grant proposals and in your press releases, you talk about the things on the end. But when you get up in the morning and come to the lab, you just want to see things that make you go, huh, right? Am I right? You know I'm right. You look at things you say, nobody's done this before, let's go do that. Or, I wonder what would happen if, fill in the blank, right? Or, maybe more to the point, let's consider, a lot of times, some brilliant person or persons comes up with a new instrument that can see things in a different way. Now you've got something new to look at. If you're the first person who looked at Jupiter through a telescope, you're not, but suppose you were. You see moons of Jupiter. That's new. Let's go take a look. That makes you go, huh. If you're the first person to shine a super fast laser on a molecule and you go, oh my gosh, I'm seeing the electrons move around in here. That's something worth investigating. Or if you take something familiar and put it in unfamiliar circumstances. If you raise a gas to 1,000,000 degrees, then you get a plasma, and a plasma is its own thing, and you got to go figure out what that is and what's going on. Here, today, I'm going in the other direction. What if you take a familiar thing like a gas, and you lower it to some stupidly low temperature? We'll call it absolute zero. It's a hair tiny bit above absolute zero, and that's okay. But you get something different. And the way to emphasize what's different down there at the low temperature is to compare with something that's more familiar, namely air. Air is a gas that I'll wager you're familiar with at some level. It's here now in the room with us. And so as we go along, I'll be comparing our ultracold gas to air to see what's different and novel there. And so an alternative, probably a better title for this talk would be, this is not your grandfather's gas. There's something new here. Oh, here I show the faces of the shiny, happy people who made the discoveries I'll be talking about today. I am just their spokesperson, and if they're here, I apologize in advance for the usual things, for oversimplifying. If you have questions, ask these guys. So what we'll do in the course of this, just to keep track of the difference, I'll make a table here, and I'll put properties of air on this side and corresponding properties of the ultracold gas on that side, just to keep track of things. I will also say this is a very vast field. Lots of work has been done in ultracold gases. There are many, many results. I'll just have a few here today, a few of our more recent ones. And I'll start with the most basic, obvious thing that's already on your mind and is bothering you. I know that if I take air and I try to cool it down, it turns into a liquid. And it doesn't have to go very cold. Like, I think it's 80 Kelvin. I don't really remember. But you can liquefy gas at 80 Kelvin. You can have trucks driving around on the freeway that say liquid air on them. And you think, well, but the ultracold gas is much, much colder than that. What gives? How can there be anything here to study at all? And the answer, my friend, is blowing in the wind. Look. The ultracold gas remains a gas at absolute zero. If we look at air, this is our first point of comparison. Here's a schematic view of a picture of air. It's the blue of a summer sky. And the thing I want to point out is that in every cubic centimeter of air, there's something like 10 to the 19 air molecules in there. That's a lot. And so when I cool it down, how does gas become a liquid? Well, the molecules in the air have to find each other because a liquid has cohesion. And they need to find each other, and they need to clump together. And there's lots and lots of air molecules here. They're easily able to do it by 80 Kelvin. If I go to an ultracold gas, here depicted as a much fainter thing because it's a lower density, you see. In every cubic centimeter, there's something like 10 to the 13 gas molecules in here. Varies from one experiment to the next. But the point of comparison here that I'm going to hammer on through the whole talk is these gases we're talking about are 1 million times less dense than air. And if you cool them, and you've got to be really careful how you cool them. It took people decades to figure out how to do this correctly. But if you do it correctly, these molecules, there are not a lot of them. They can't find each other easily and clump up into gases or solids. They remain gaseous at absolute zero. There are experts here who know that I'm glossing over a lot of details here. That's part of the fun. All right, so the ultracold gas remains a gas. Let's look at what the constituents of this gas are. What's going on inside the gas? Well, air is made up mostly of nitrogen. Here are pictures of nitrogen molecules here. Nitrogen molecules are blue, and that's why the sky is blue. That's a lie. That's not true. The sky is blue because it reflects the blue ocean. No, that's also, never mind. Here are molecules running around in gas, and you can see each molecule, these are diatomic molecules. If I look at any particular molecule here, well, it has a direction. It wants to point in this way. Others can have different directions, but the real problem is they're moving around really fast. They bang into each other, and even if this molecule had some well-defined direction at some point, later on, bang, something hits it, and it rotates around. There is no preferred direction, no preferred orientation of the molecules in air. Contrast that to the kinds of ultracold gases I'm talking about today. Here we have diatomic molecules with two different kinds of atoms, like this model molecule right here. There's a blue atom and a red atom, and they're different. And of course, each molecule has a preferred direction and orientation. If you let them go, they would bang into each other and do the usual thing. But here's the trick. Of course, this molecule is polar. It can be a little bit positive at this end and a little bit negative at this end. And it means that if I do the following, I'll put two metal plates, one above and one below, and they're connected by a battery. So there's a voltage across here. There's an electric field across here, and the response of the molecule is going to be to line up in the direction of the electric field. And that gives the gas a direction. All the molecules are pointing in the same direction. And you'll say, yes, but here's my molecule pointing in this direction. Another molecule comes by, and isn't it the same old story? This molecule will hit it and start it spinning and wreck that orientation. And the answer is no, because this gas is really, really cold. And so this molecule hanging out here, if it meets another molecule, it's moving really slowly. And it doesn't have enough energy to disturb that orientation. Part of the fact of being ultra cold and polar is that I can define an orientation inside the gas. This is one of the main things we'll harp on for the rest of the talk. Okay, so gas is isotropic. Ultracold gas can be anisotropic. And that matters because, as you know, we have little dipoles here, and I have a plus end and a negative end, and it's the electrostatic analog of ordinary magnets, of the kind that you've played with many times, with north and south poles. And you know what happens if I take two magnets and I try to bring them close together, they resist. There's a force of repulsion between them, and that will matter. But if I bring them like this, they attract one another. The north pole is attached to the south pole. The positive charge is attracted to the negative charge, and they go tink. And so we have little dipoles, and the interaction between the little dipoles depends on their relative orientation. And the way molecules interact is what gives you the properties of a gas. For example, let's talk about sound. Here's a schematic picture of sound. This is our blue air. This is what sound and air looks like. Your irritating neighbor has a speaker going at 1 in the morning, and the cone on the speaker is going wah, 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 and it's pushing on the air periodically. And you know how this goes, right? The speaker goes wah, and the air there goes to high density, goes to high pressure. And air says, no, I'm not going to be at high pressure. I need to release this pressure. And it goes boom, and relaxes like this. Oh, no, but then it goes to high pressure over here. No, no, no. And then it goes to high. So there's this pressure wave passing through the air here, governed by the fact that the air doesn't want to go to higher pressure. And that sets the speed of sound. In the ultra-cold gas, look what we can do. Here's my gas. It's the faint colored one. That's how you know it's ultra-cold. Here are the molecules. Here are my field plates here. Gosh, you know what? These look like they're made of gold. This must be from Jun Yi's lab. And now I haven't shown the speaker here, but let's imagine I'm propagating a wave here. You see it's low density here, it's high density here. And what happens is, when the molecules are forced to go to higher density, and if they're polarized this way, when they go to higher density, they find themselves side by side. They're repelling each other. They want to get away from that situation, spring back. That springy action makes the speed of sound faster. Faster compared to what? Well, the other case, where now I've got my plates this way, I've got my dipoles polarized this way. If they come together at greater density, they're more likely to find each other attractive. The molecules go, hey, I kind of like that. I'm not going to spring back so readily. And so in this case, the speed of sound should be lesser than in the other case. That is to say, the speed of sound depends on the direction of the dipoles relative to the propagation of the sound. And here it is. So now we envision an experiment. In this case, the sound wave is traveling left to right. I've got the field plates. I can tilt them at some angle with respect to the direction of propagation of the wave. And what do you know? Here's the speed of sound as a function of that tilt angle. Speed of sound is really slow, centimeters per second, in a gas this dilute. And here it is. At 0, when the things are polarized in the same direction as the propagation of the wave, speed of sound is relatively fast. When they're polarized perpendicular, the speed of sound is relatively slow. Sound is anisotropic. Imagine what this would be like. Suppose you sprung for excellent seats at a concert, and you're sitting dead center in the concert hall. But on the night that you arrive, they've replaced the ordinary air with ultra-cold gas polarized in this direction. Well, bring a jacket, first of all. And now the concert starts, and the sound over here coming from the violins, the strings, comes at you faster than the sound coming over here from the reeds. What an awful discordant mess. You're thinking, you need to get your money back for these tickets, and not to mention the fact that they're watering drinks in the lobby. So sound can be anisotropic. Here's what's interesting. If I raise the temperature, so this gas is at 250 nanokelvin, 250 billionths of a degree above absolute zero. And that matters because if I increase the temperature a little bit, I'll turn it up to 1,000 nanokelvin, and the effect is different. The overall speed of sound is a little faster in a warmer gas, and the variation with angle is lesser in the warmer gas, because the difference is between the energy of repulsion when the things are doing this versus the energy of attraction when the things are doing this. In a hotter gas, both of those kind of pale in comparison to the kinetic energy that's flying around in the gas. So the relevant thing here is that comparison between interaction energy and temperature. And so if I go much warmer than this, this effect goes away. So here's something that happens in the ultra-cold gas, and it had better be damned cold in order to make this happen. So that's worth putting on the sheet here. Sound is isotropic in ordinary air and anisotropic in this gas. Oh, this thing about the concert hall reminds me. Air is easy to come by. Here is air. You've seen it, well, you've experienced air your entire lives, I presume. The ultra-cold gas is not a thing you find in nature. You've got to specifically prepare an ultra-cold gas in a thing like this. I'll put this up. This is, whoops, sorry, exists in a special environment, which is this. This is a picture from Jun's group. They have potassium rubidium molecules in a setup like this. This is an extreme close-up. And where the molecules are, where the action happens, is in the center here, which is a little glass box filled with nothing. And it has to be a glass box because, well, you need to be able to see in there. And also because the way you produce these molecules, the way you manipulate the molecules, is to bring lasers in. And so you need windows that are clear to laser light to make this work. And there has to be nothing in there. It has to be extremely high vacuum, because if you left ordinary air in there, it would wreck everything. Ordinary air liquefies at 80 Kelvin, and you would get it on the, I don't know, it would smear all over the glass walls of the thing. I don't know, it would be a mess. I don't actually know what would happen, but it would be bad. So there's a vacuum there. You let in just the molecules you care about and do what you want to do to them. Then they're surrounded by, I don't know, that looks like a magnetic field thing. There's a wire, I don't know, and then it sits on a big table with lasers and lenses and probably even more aluminum foil than you see here. I don't know. That's not my thing. My thing is what's going on in here. And what's going on in there? Well, we often think about this ultra-cold gas schematically in sort of an oval shape like this, because here's another difference. It didn't even make the list. If you wanted to carry around air with you, you'd put it in a bottle, let's say, and there are glass walls on the bottle, and they confine because the air molecules go boink, boink, boink off the side of the bottle, and that's confining. This little glass cell in the middle of Jun's experiment is not like that. That's not the walls. The gas doesn't go all the way out to the walls. The walls are at room temperature, so you've got to hold them somehow deep inside this empty glass box by means of lasers. And what happens is this oval is meant to give some rough indication of the places the molecules are free to go. And so they can, in this case, they can travel a greater distance up and down than sideways. That's all it's meant to convey here. And inside of this, rather than bouncing off the sides of the wall, they execute motions more or less not unlike the motions of this sample molecule swinging here in front of you. There's no wall here, no glass wall. It's just, well, it comes to a point in high potential, has to turn around and go back the other way. Or it can run around in a circle too, see? Now you're having a girl, congratulations. Right? And basically this is it. So this is, the molecules can run back and forth in the trap like this. If there are really very, very few molecules, that's all they'll do is run back and forth. But there are other molecules. And every once in a while, whoops, whoa. Oh no, did you see what happened there? What a dramatic and effective demonstration. Here's my molecule minding its own business. It sees another molecule, and it goes scattering off in some other direction. And that sets properties of the gas. And that's relevant to the topic of rethermalization. So another thing that sound waves can do in air is become attenuated. I have these increasing pressure modulations in ordinary air. When air compresses, there's viscous forces or whatever, and the energy in the wave will eventually attenuate or dampen. Why they call it dampen, I don't know. It sounds like you're getting it wet. But energy can be dissipated, and the same is true here. So I'm not going to exactly call this a sound wave. It isn't like that. But let's look at it. Let's look at it for what it is. Here's my gas of molecules, and I take. It's not really stereo speakers, but there's some means by which you can pump a bunch of energy into the vertical direction, whomp, and you start the gas going like this. Well, it can't. And then the important thing is you stop doing that. You've taken it out of thermal equilibrium. The gas is going like this. Thermal equilibrium has the gas sort of as a whole, sort of more or less motionless. And what will happen is all the energy that you put in this direction by collisions of the molecules will be scattered off into other directions and heat up the other directions while this one cools off. That's what rethermalization looks like. And the, and the sound waves ultimately die off. That's a cute graphic. And here's what it looks like. This is a simulation Ruben did. So you hit the gas, bwomp, sorry. You don't hit it that hard. Bwomp, and you start it off, and this is temperature, or strictly speaking, some kind of mean energy, because then I can split it up into the three directions. So this is versus time. So up here, as soon as you go bwomp, the temperature of the gas in the vertical direction is very high, and the temperature in the other two directions is more or less what you started with in this gas. And then you stand back and watch what happens. And what happens is thermal equilibrium. So the thing that's hot has to cool off. The things that are cool have to warm up. And eventually the whole thing comes back to a uniform temperature. You've heated the gas, but what's important to us here is the process, the getting there. The rate of thermalization is a statement about the non-equilibrium dynamics of the gas, if you want to look at it that way. And here, the thing is, it's very orderly. I look at this and I say, well, basically this temperature just goes down and down and down. I can see it wiggling like this because I happen to know it was wiggling like this. It's in a harmonic oscillator trap. It really is doing that. And the collisions are infrequent. And so I see the overall motion superimposed upon the damping. This is the effect of having a dilute gas. In the other directions, I see these heat up in a very straightforward way. They also oscillate. And the other thing is, in this case, the gas is like this. I'm exciting it like this. Bwomp. The dipoles are pointing over here somewhere. Maybe over here. Probably over here. And that sets an anisotropy between heating up in this direction and heating up in this direction. And in fact, you see that. The green direction here heats up faster than the blue direction. This is anisotropy of the rethermalization of the gas. I will say, in passing, this is actually a useful thing, because one of the things you need to know in order to understand the property of your gas is how hard the molecules hit each other, or more specifically, the collision cross-section. Two molecules approach each other, they scatter off in some direction. How likely are they to do that? And this phenomenon, is entirely due to collisions. The only reason this damps is because the molecules are running into each other, as you saw in the beautiful demonstration earlier. And therefore, if you know how to read plots like this, you can extract cross-section information from experiments that do this. And Ruben knows how to interpret things like this. And it really, really works. We have worked with the Ferlano group to extract cross-sections from some of their molecules, well, it's atoms in their case, by using tricks like this. But that is not all. You know where I'm going with this, right? There's got to be an anisotropy here. So here, I have the gas. The gas is vertical. I'm going to excite it in the vertical direction, bwomp, and set it going like this. It's going to relax, just like in the previous figure. But now, I go, oh, look, I take my electric field plates, and I tilt them with an angle with respect to the direction the sound wave is propagating, the direction of the excitation. And now I'm changing the preferred axis of the gas defined by the dipoles. Surely the collisions of these things are different if they run into each other in different directions because the tilt is different. And therefore, we expect that the rethermalization rate should depend on this angle. And it does. Here it is. So here, this is a plot of, this is more or less the time it takes to rethermalize, the time constant of that decaying curve we had before, as a function of the angle here. And this is in weird units, don't worry about it, but 3 is bigger than 1, right? That's kind of the point here. So it's a sort of, whatever, 50% change in the rethermalization rate just by turning the dipoles. This gray curve here is not even the result of an elaborate simulation, although one can do elaborate simulations of this. It turns out in this case, in the dilute gas, Ruben here can come up with a formula for this. Let us call it Ruben's gas formula. There is nothing of which he is more proud. And it's a crazy formula, but but you know, there it is. It predicts the variation between 0 and 90 degrees. These dots here are actual data, again from Jun's group, where they did this experiment, and the agreement is kind of amazing there. It's a real thing. You can alter the rate of return to equilibrium by so simple a device as changing the direction of the field. That's a thing that makes me go, huh. This is where the fun starts. All right, so here we have control over the approach to thermal equilibrium, and more generally, one supposes, if we lean more toward the application side of physics, now you're controlling something, you can think about manipulating thermodynamics to do the kinds of things you want to do. That's an old story. In ordinary air, I'm kind of glossing over this, but in ordinary air, or let's say steam, it's a very typical thing to control the thermodynamics and make something useful happen, steam engines. So who's to say we can't not build an ultra-cold steam engine out of this? We're looking for investors now. All right, so that's part of that story. Now, we can extend this story a little bit and go to even a different regime. We say, well, here's a gas, and the gas is 1,000,000 times less dense than air. The molecules more or less don't see each other. They see each other rarely, and we can track that behavior. But now you can also imagine turning up the density a little bit to make them collide a little more frequently. Or equivalently, if you go to something with a larger dipole moment, they have a larger collision cross-section, and you can go from this regime that we've been talking about, which we call gas, where the molecules, just to remind ourselves, the molecules are pretty free to just wander the length of the confined area, back and forth like this, and once in a while run into something. And that makes the problem really tractable. If you go to higher density, it's a different story. This thing is trying to make an excursion across the entire trap, but there's molecules everywhere, and it goes boink, 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 right? And it becomes a much more local thing. Very few of the molecules actually make it all the way across the trap. They're running into each other. And it's a very different physical picture. It helps, right, to have the okay. It's a very different physical picture. You don't talk about a gas with free molecules occasionally collision. You talk more about something like a liquid. It's not a liquid because it's a gas 1,000,000 times less dense than air. But in some ways, it behaves like a liquid. And I don't think about the global thing and the molecules going like this. I think about what's going on right here in the gas because the molecules are running into each other. And I ask myself, what's the density profile? What's the velocity field? In other words, I think of it in terms of fluid dynamics. I think of it in terms of Navier-Stokes equations and things like this. It's a completely different regime to be in. And the thing is, experiments are pretty close to getting into this regime. They're getting really good these days at making molecules really, really cold. In some extent, the hydrodynamic regime has been seen, has been touched in these gases. So what's the kind of thing that will happen? Here's an example. Here's our favorite experiment. So now in the hydrodynamic limit, I take this gas, I go bwomp, and now instead of molecules going like this and colliding, it's a fluid going whatever fluids do. And it's the same plot here, in fact, with the same color coding. Here I have the relative temperature in the 3 directions as a function of time after the pulse hits. The vertical one starts with a lot of energy, because that's the one I kicked. These two start with relatively low energy, the sideways ones, because they're just what they were. And now, this is something very different, something very irregular. You remember in the previous picture, the hot side just kind of drifted off to thermal equilibrium. Now it's wobbling like crazy. The energy goes down, it comes back a little bit, it goes down, it comes back up more, goes down. It's very irregular in this way. And the same thing with the things in the other directions. It's a fluid that's going like this. In fact, I know what this reminds you of. It reminds you of the surface of the sea, where, so here you have waves, but if you watch, and this is a still picture, I'm sorry. I couldn't get a good video. You know, last week I was in Sorrento, Italy, and I thought, well, I'll take a nice picture of the waves and try to see the motion I'm talking about. but the Mediterranean is just so calm in Sorrento. And I guess the only point of this story is I was in Sorrento last week. But you know what I mean. You look at the surface of the water, especially when there's a storm coming on, things are rushing. The water goes high here, and then high here, and then a little less high, and it's irregular in this way. It's irregular in the same way that the fluid motion of our droplet is here. And this motion is called weltering. So there it is. So now we're advancing the proposition that somebody should measure weltering in this gas. Look, I'm not making this up. Here's Moby Dick, an American classic. At the very end of Moby Dick, and the third day of chasing the white whale, and rest assured, there will not be a fourth day, right? I mean, it's about to hit the fan right here. Things are going bad. The sea is rough. They're trying to find this damned whale, and there are sharks in the water, and they keep breaking oars, and things are going bad. And to describe this, Melville says, with a mighty volition of ungraduated, instantaneous swiftness, the white whale darted through the weltering sea. And he gives you this picture that things are not great here on the surface of the ocean. And this gives you the impression things are not great in the fluid, in the ultra-cold gas. I guess that's not the point I really wanted to make. But it's a different physical regime, different things go on. And once you're in this regime, now it's a fluid. Now you really do think of things like, you know, there's a viscosity to this fluid. I have to think about it in those terms. There's a heat conduction tensor that runs through there. And all of these things depend on the direction of the orientation of the dipoles. This is still a fluid with a preferred direction. We are at the very beginning of understanding that. So there's much more to be done to carry on this and see what these fluids really do. Weltering is the first step. Hmm? So the waves, yeah, this is a bad picture. The waves, of course, are moving unidirectionally. But if you're out in the open sea, you're not seeing the waves break on the shore, and there's a storm, right? It's just water randomly going up and down in the waves. Yeah. I just couldn't find a good movie of this. But I will add, weltering is also used to describe what pigs do in slop. So make of that what you will. So this is the beginning of some new set of investigations. Let's take it, okay, and so what have we got? The ultracold gas can exhibit weltering motion in the hydrodynamic limit. Air doesn't do that, right? You go to a different thing, not a gas, but a fluid, to see this kind of irregular weltering motion. It's nonlinear evolution of the thing. Let's take it one step further. So we've talked about, you can start with a gas over here. Gas is tractable, does simple things you can try to track. The fluid is, in a way, much more interesting, much more phenomenology going on. We don't know yet what all is going to happen. There will be turbulence and all sorts of things. We can go to yet slightly higher density or yet slightly lower temperature and enter the regime of the Bose-Einstein condensate, which you may have heard of. And there's a definite transition between the center thing and the right-hand thing. We talk about viscosity in the weltering fluid. By the time you get to the Bose condensate, no more viscosity, right? It's all quantum mechanical, whatever. I'm not going to go into that. But I will point out, the first Bose-Einstein condensate was discovered in 1995 at Rice University. No, that's a lie. That's a good-natured... I'm uninvited now, aren't I? Here in this building was the first Bose-Einstein condensate. It generated a slew of fascinating research. In the last 5 years, there's been an upsurge in Bose-Einstein condensates with dipolar particles of the kind I'm talking about here. And the phenomenology is absolutely extraordinary and broad. We'll focus on just a couple things here today. In the Bose-Einstein condensate, you don't have, sort of gas kinetic equations. You don't have Navier-Stokes equations. You have quantum mechanics. You have Gross-Pitievsky equations. And the whole thing is about minimizing the energy. So what can happen in there? Here now we envision an experiment like this. Now, I've turned the gas on its side because that's relevant to these experiments. We don't really need to go into that. But I've filled this space with molecules. I've got them polarized with my gadget here. Excuse me. And they're pretty free to move around. You don't really think of them as colliding in this, as more or less sliding over each other because there's no viscosity. They're free to go wherever they want to minimize the energy. And these are dipoles, and the dipoles go, well, all right, challenge accepted. If you're going to polarize me in that direction, side-by-side dipoles would prefer to repel. And so we can reduce the energy by sending some dipoles over here and some dipoles over here, so there's distance between them. And that minimizes the energy. But then you'll say, no, 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 you can't fool me with that, because by doing so, I've put a whole bunch of molecules here. Don't they repel? And the molecules go, yes. But under some circumstances, we are free to line up in this direction. We're free to go to JR. What have I done?
We've lost video.
Ten to the 19.
There it goes.
Oh, excellent. Thank you.
No problem.
Thank you very much, because these, right? JILA. And this is good, because the coolest pictures are coming up. So the story is, well, how do these dipoles want to minimize energy? They get away from each other, but there's a bunch of them. So when they meet other ones here, they minimize the energy by elongating this way. And so the gist of it is, you get, under the right conditions, it doesn't do this just all the time. This is under very special conditions that I won't bother to elaborate on, but you'll get density here, density here, density here, and nothing in between. That is to say, you will get a gas 1,000,000 times less dense than air with lumps in it. And you go, come on, right? This is yet another idle theoretical fantasy. Not so. Here's an experimental picture from the Francesca Ferlano group in Innsbruck. Look at this. This is an image of atoms. Okay, all right. The atoms are highly magnetic, so they have dipoles, and you can do this kind of thing with them. And in this case, there it is. This is a picture from this point of view. You're looking down from this direction. They're polarized by magnetic fields rather than electric fields, but none of that matters. The point is, they really do arrange themselves into a thing like this. The bright colors are high density, and the background is fairly low density. And so not only do they rearrange themselves into a lumpy structure, but the lumpy structure has a periodicity. This has a six-fold symmetry, more or less, running around the central object there. It blows me away that a gas can actually do a thing like that. There are predicted to be many, many, many other interesting shapes that occur under different circumstances, these things. In a way, this is the basic one. This is a Bose-Einstein condensate that is a superfluid, something that flows without resistance, but it also has a periodicity like the atoms in a piece of aluminum. And so it is called the super solid. Get it? It's super, and it's like a solid. People argue over whether that's a good name for this, but I'm not going to. I'm going to call it a super solid because it's cool. And there it is. And so the point is, the ultracold gas, if you arrange things just right, the gas can be lumpy, can have bumps in it, can have density variations in this extremely tenuous gas. The air, not so much. I mean, this is in equilibrium. Of course, the sound wave changes the density of air as it moves along, but that's not what we're talking about. This is an equilibrium situation. Now, Hui, who's sitting over there, poses the following question: what if you had two of these things? So the picture is something like this. This is a calculation now. This is not data. But here it is. You've got some situation where I see the six-fold symmetry just like we did in the experiment a moment ago. This is looking down from the top. Here we're looking at it from the side, and there's one above and one below. And this is achieved because we imagine the excuse me, the the confining potentials that hold this gas in place have a minimum up there where this one is sitting, and another minimum down here where this one is sitting. And in between, there's some potential barrier that these things cannot surmount. And so they're kept separate from one another. That's fine. You can certainly do that. It's no shocking surprise that in two essentially separated potentials like this, you can get what you would have gotten in any one of them. But even here, you can see, look, this central piece, which is the highest density thing, this one's already reaching out toward that one, this one's already reaching out toward that one, because the dipoles are polarized vertically like this. They are still attracting across space. It's just that this one is not touching this one. And so then you go, well, what happens when I push them closer together? I bet you can guess. But the picture shows this. Now they come closer together. The barrier has dropped a little bit in the middle. They are capable of tunneling from one to the other. And atoms run into the middle here at the expense of, you can see it's relatively dim. Well, I don't know if you can see that. Atoms from these peripheral things go into the center, run down to the middle here. This is where all the atoms are. And so now what you've got is a tendril of Bose condensed gas running from below to above. And inside the tendril, you have dipoles, and the dipoles are all attracting each other. And so there's a kind of, I guess, a kind of cohesive energy that holds this tendril together. And if you bring them closer together, other things happen, but I won't dwell on that today. But just the difference between this and this is interesting, because now you say, well, this is an equilibrium situation. I can say, or Hui can say, here's the energy of this gas at a certain distance, and here it is at another distance, and here it is another distance. The derivative of energy with respect to distance is the force. That would be the force required to pull these two things apart in the presence of this tendril. And he calculates that, and it looks like this. This to me is an amazing diagram. It makes me go, huh. So what I have here is the force, and here's the distance between the lower and the upper in microns. I realize actually this is half the distance because I'm measuring from 0. Never mind. But they're sort of microns apart. The force is measured in yoctonewtons. Yoctonewtons. And you think yocto sounds like the name of one of the Animaniacs. But what it actually is an SI prefix for 10 to the minus 24. It's a I don't know, it's small. I don't know of any other thing that's given it. I don't know why they have a name for this, frankly. Okay, I'm sure somebody uses it for something.
If I turn the top picture on the side, I would expect 5 things, not 3 things.
Oh, this is, sorry, you're right. This is a slice through the middle. So you're seeing the middle thing, and it's oriented so you see 2 things on either side. And
So I don't see the 5.
right, there's one in front and one in front, and one behind and one behind. Yeah, thank you for that. All right, and so here's what the force is doing. As we pull the things apart, the force itself is getting lesser and lesser and lesser, and then something dramatic happens there. What's happening is you pull on these gases, you raise the one above the other, the tendril gets thinner. There are fewer atoms in there, fewer molecules. And when there are few molecules, there's less dipole attraction in there, and the force goes down on that account. And you get to the end here where this kink is, suddenly that's the point where the lower part detaches from the upper part. The tendril no longer goes all the way through, and they're 2 separate things. And so there would be no force at all, except, well, there's some residual force. There's dipoles up here and there's dipoles down here, and they do see each other from a distance. But they see each other differently when they're connected by this tendril. It reminds you of something. It reminds me of something, and that something is silly putty. Look here. If you've played with silly putty, you know exactly what I'm talking about. If you haven't, I have some here. Come play with it. So here I have a more or less cylindrical piece of silly putty. I'll put out my sleeve, and I start pulling on it, and it takes a certain amount of force to pull this thing apart. But then it's a plasticine material. It gets thin in the middle, and I can feel it. It's much easier to pull apart now because there's less stuff in there pulling. And pretty soon, eventually, it breaks. It breaks. And there's a transition, and then there's no force between them at all. That's what this gas is like. This is a gas 1,000,000 times less dense than air. and it stretches like silly putty. And there it is. This thing, this gas has this property of, oops, oh my goodness. And what's the analog of that for air? What do you even put there? I have absolutely no idea. I don't even know what it means to grab air and pull on it and ask what the force is there. So this is something that this ultra-cold gas we expect will do that air cannot do. We have not yet figured out how to use it to lift pictures out of the Sunday Funnies, but we're working on that. And at this point, I've run out of room to put more things on my list. So I think I'll just leave it up as a summary slide, and I'm happy to take questions. Thanks for your attention. In this case, it's six-fold symmetry because of the size of the harmonic potential we're holding it in. So there's a balance of forces. These bumps repel each other with a certain energy. There's a certain energy confining them in it, and it finds the balance between those. If you lowered that potential and let it spread out more, you could get alternative shapes with more bumps in them. But the fact is they repel, so they form a lattice, much like a Coulomb crystal.
What was the material? You said it was magnetic?
Oh, so in the experiment I showed there, a couple slides back, that was erbium. And erbium is, I know it's down at the bottom of the periodic table somewhere, and it's one of the most magnetic of atoms.
John, so in this tendril, do you see a sort of Josephson junction-like phenomena where there's a tunneling current which depends on the phase difference between the up and down, or did you minimize this by locking the phase together?
Write that down. What's done so far, this is uniform phase all through. This is just the solution to the ground state of the Gross-Pedievsky equation. Uniform phase everywhere.
Okay, but you could also minimize the energy where you just make a pipe onto phase offset, and
we could.
You should see them sloshing back and forth.
We could, but we have not, but we will.
Stretching experiment, or not experiment, simulation. Why you have to be super solid? What feature of super solid is used here? I can imagine you do for superfluid phase. You can do same kind of experiment too.
No, you're absolutely right. It's presumably does not have to be a super solid to start with this. But that happens to be what we're investigating, and we saw it, and we're running with it. The original idea was, well, you've got six-fold symmetry here. What if you start this rotating? You know, is there a torsion in there that could start the other one rotating? Or maybe we'll build a phase difference in. So that's just what we've been working with.
Oh,
One presumes a similar thing could happen
Okay.
In a regular BEC.
Yeah, thank you.
Thank you for this. Is a fascinating talk. When you were talking about the weltering motion, it made me wonder about how that might also depend on the dipole alignment. But it also probed the question in my mind: how do you quantify weltering if you wanted to look at the difference there?
How do you quantify weltering? So you touch on an important issue here that I glossed over because I didn't think anybody would be this sharp. Look. In this case, so in the previous case, one thing that happened was I had the elongated thing, I had the dipoles leaning in this direction, and there was a difference in the heating in this direction and this direction because those collisions were relatively infrequent. Here, the blue and the green are the equivalent things. There's very little difference between them here. And it's because, in the gaseous case, here we have molecules, all they do is come from this direction, hit each other, and go like this. In the fluid, they're doing like this all the time. And whatever effect you had in that, because of the dipole orientation, quickly averages out. And that's what we're seeing here. How do you quantify weltering? I don't know. But it is also true that the very first activity here, after you kick it, the early time stages of this do depend on dipole orientation. And there's a whole big story about that, because when you model this, it's fairly high density in the middle, but these are held in a harmonic oscillator trap. The density goes down at the periphery. So it's hydrodynamic in the middle and gaseous at the periphery. Well, that complicates things, and part of the complication there involves the direction of the dipoles. In ways talk to Ruben for more details.
Thank you.
Thank you.